Okay, so hi everybody. I hope everybody is hearing me. So welcome to the third webinar of ECO. And we can start now. I just leave the floor to Dibyajyoti Ghosh for perovskite materials for solar cells.
Okay, thank you. Can everybody hear me? I think so. And okay, let's start. Okay, so I am Dibyajyoti Ghosh. I am a research associate at University of Bath and working with Professor Saiful Islam and Professor Alison Walker here. And my main research interest is to find out new solar cell materials which will be much more efficient and cheap in cost, so that it becomes much more easy to use the solar cells. So in this webinar, I'll be as title suggests, I'll be mainly focusing on the atomic scale insights of perovskite materials from ab initio modeling. And here, as you can see, this is the brief outline of my talk. First, I'll give an introduction about what the energy sources we are using and what's coming next. That's kind of we can have energy crisis here. And then I'll introduce a bit of photovoltaics and particularly focus on the perovskite solar cells. Then I'll come to the main topic of my discussion, that is metal halide perovskites. There I'll touch upon two main factors, main topic of my research, that is stability, electrostructural dynamics and electronic properties of different type of compositionally engineered perovskite materials, and also how the phase transition affect these properties of perovskites. And then I'll focus another part of my research, that is lead free materials, how we can replace lead and with different type of other metals to reduce the toxicity of perovskite materials. So let's see. If you see, we have this is the energy consumption by the entire world in 2013, and as you can see, still we mainly use petroleum, natural gas and coal as the main source. This is 86%, and that is, as you know, all these are fossil fuels, so you cannot reuse it. You just burn it, get the energy, and leave the product like carbon dioxide, which is bad for the environment. And only we till now we only managed to use only 10% energy from as the renewable energy sources. So as you can see, the main energy is still coming from the fossil fuels, and as the source of these fossil fuels are very limited, you can clearly understand that very recently we'll have the shortage of these sources. Like as you can see in these, it's an American mining area where it finished its entire coal reservoir by 1960s. And also you can have a crisis in oil, gas, and entire these all non-renewable sources can entirely finish up its storage. So we really need to think a different way of getting energy for our usage. Not only the shortage of the shortage of these sources, we also have problem regarding the environment, its environmental effect. Like when we burn these fossil fuels, we generate CO2, which increase the energy temperature of these atmosphere. So we have a kind of environmental problem also. And as you can see, the temperature anomaly is going higher and higher in from last 3 or 4 decades because of that. Also, we can have different type of natural calamities like the burn down of these big forests, or you can have flood, and also the melting of the ice, which can eventually cause a huge amount of increase in the sea level. But as I told, there are other sources from these fossil fuels which can be used, like renewable sources. So main, as you can see, it's only 10% in use, but still you can you have different sources like solar energy, biomass, hydropower, etc., which can generate energy, and you can use it again and again, and these are kind of will not finish, just like fossil fuels. Just to see where we are in UK, we are doing pretty good. In 2016-17, we have used 30% of our usage came from the renewable sources, and we are really reducing the coal particularly. And but still we have gas and nuclear as the other major sources of the energy. If we break down these renewable sources, you can see mm, major part comes from the wind, but still we have 17% coming from solar photovoltaics. So that's kind of encouraging for us to do some research in this particular area, and that's motivated us to look into the current scenario of the photovoltaics. And if you see the solar cells, it's basically 3-step processes. So typically you have a solar cell, and where the light when the sun shines and the photon get absorbed in this material, you have type p-n junction type. So the photon excites the electron, that is because of absorption of sunlight, that is the first step. Then it excites the electron from valence band to conduction band, so that is separation of charge carrier. And then if you put load outside in your circuit, then it will you can extract that electron flow as your electricity. So as a whole, that is the extraction of carrier. So these are the main 3 processes by which the solar cells generally operate in a simplistic way. Also, if we see the materials, this is the famous NREL chart, and as you can see, it's pretty much all the materials which have been used as a photovoltaic materials has been listed here. And we can see that there are quite efficient, highly efficient materials are there, but they are very costly because of their manufacturing and very difficult architecture. So it can be multiple junctions. But we are interested in some little part of it. It's perovskite solar cells, which started from last few years, and it has gone from 3% to above 22% in few years. And most interestingly, it's very easy to prepare, so you can have kind of roll to very easily and cheap where you can produce it. So that's something very interesting, and also it has kind of high efficiency, as you can see. So these attracted huge research interest in perovskite solar cells. So if you see perovskites as a structure, it has a chemical formula of ABX3, where A is a monovalent cation shown in this blue dot. So and BX3 forms this octahedra. And in this octahedra, the middle of it occupied by divalent metal, that is B here, and all the corners are occupied by monovalent anions, that is in violet dot here. So and these octahedra are connected by corner sharing in a corner sharing fashion. but the particular material which are highly used for these perovskite for solar cell purposes, it's a bit different. So it's a organic inorganic perovskite. So there you have a kind of organic molecule instead of particular one atom in the A site. And in this figure, as you can see, this is a methyl ammonium which is occupying the A site, and this is the typical example of organic inorganic perovskite which has been used for solar cells. And as I also mentioned before, it's these type of materials are very easy to synthesis. You can absorb, you can tune their absorption property quite widely by changing different halides or A site cations or B metals, and also it has a long diffusion length. So you can really extract the generated carrier very easily. It has other interesting properties also, which I'm not going into detail now. I'll come to other points later in my slides. And just to show how schematically how exactly these perovskites work, or what's the solar cell architecture. So you have a perovskite kind of absorber layer here, and when sun shines and the photon fall into the perovskite, it forms it generates electron and hole, as I told you, by doing the extraction of the charge, and then it goes to the outer surface and generate the electricity. So but this is a very promising material, but you still have various problems, like most importantly, these perovskite, particularly the hybrid perovskites, degrade very quickly at ambient conditions. It contains lead, so it's a toxic in nature. And then you have the intrinsically, we have found that ions inside it migrates very fast. So you can have ion migration here, and because of all these factors, it's very challenging to upscale it and reproduce it in a commercial level. So and also very intrinsically, it has another something interesting property, that is its lattice is very dynamic in nature. So if you see, if we do a molecular dynamics simulation, we found that periodic octahedral tilting, periodic octahedra, its octahedra tilts periodically, and also the inside it, the organic cation tumble and liberate, so that so as a whole it's a kind of dynamical lattice in nature. And these dynamics can affect the photovoltaic properties. Like it can have people have hypothesized that these type of dynamics can have effect in band gap. So it can have direct or indirect band gap, or it can also affect the PL efficiency of these materials because of this structural dynamics. So we look into this problem, and we first look into the stability dynamics in a compositional engineered materials of these perovskites. So people have found that if we mix different size cations in a particular ratio, then you can enhance the stability. So just for an example, if you have methyl ammonium as just a single cation in this methyl ammonium lead iodide bromide, so it degrades very fast. But if you mix a bit of formamidimium and cesium, surprisingly you find better stability. Also different group came up with different type of ideas or reasonings. So it can be higher dipolar interactions which is enhancing the stability, or it can be the entropy of mixing, which is increasing and giving the stability. With all these in background, we started our research and trying to answer these following questions. First, we try to find that what's the effect of the overall structure because of this cation mixing, and whether we can find some other factors which are giving the extra stability to these lattices because of cation mixing. And also later we also studied the structural dynamics and electronic properties of these mixed cation perovskites, and tried to found that tried to find that how exactly is cation mixing affecting these properties. So for our study, we have taken formamidimium lead iodide as our parent compound, as you can see here, and some of the formamidimium has been substituted by cesium or rubidium or methylammonium to have kind of mixed cation systems. As a method, we have used ab initio molecular dynamics to capture the real-time dynamics of these systems. In this method, we calculate the forces on the fly, and then we solve the Newtonian equation of motion to get the atomic nucleus, to time evolve the atomic nucleus. And as a simulation parameter, we have used supercell of considerably large as a cell of formamidimium lead iodide, and we have simulated an NP2 ensemble at 300 Kelvin. For static calculations, we have used density functional theory based code, FASP, and there we have used PAW methods, PV-solve functional we have used, and to look into the different type of particularly electronic properties, we have used spin orbit coupling for some of the calculations. So let's see what's exactly happening when we are mixing different size A-cations, and we found that when we mix different A-site cations in formamidimium lead iodide, the whole volume of this cell get reduced. So and if you take these particular 3 bars, you can see the amount of this contraction in the volume is directly depend on the size of the A-cation which is getting substituted. So for example, when you have cesium which is much smaller than methylammonium, so you have a much larger contraction in the volume. So to find how exact from where this exactly coming from, we first look into the volume of octahedra, and for doing that we calculated G of R of lead iodide bond, but we didn't find any change there. So also we calculated volume of these lead iodide octahedra, and we didn't see any change with cation mixing. That signify that we don't have any internal distortion in these octahedra because of cation mixing. Then we look into the tilting of octahedra, as you can see here, and if you take the mean theta value, so you can see that it's these lead iodide lead bonds are getting tilted because when we are mixing different size cations, and that is the reason for this volume shrinkage. When we calculate the time average structure of it, we found that with FA-cations are pretty much cubic in nature. However, when cesium is there, so you find that this is the octahedra are mutually tilted, and you have kind of distortion in the lattice. And so because of this distortion, another interesting thing happens. So that is, you have a formamidimium as your A-site cation, and the hydrogen of the formamidimium and the iodine of these cage comes closer, and it forms stronger hydrogen bond. So to prove that, we also calculated the vibrational spectra of the NH of the FA-cation, and found that with cation mixing we really have NH red shift in the NH stretching frequency. That signifies the NH bond is getting weak because of stronger hydrogen bond formation between iodine and hydrogen. So and this type of hydrogen bond, as we all know, can lead us to higher structural stability for these perovskites. We also look into the dynamical properties. Dynamical property, and as you can see, first of all, we look into the octahedral motion, that is the tilting motion. Over time, it tilts back and forth. But in formamidimium lead iodide, as you can see, the fluctuation in the PBI-PB bond angle is pretty large, so it fluctuates over time. However, with cesium incorporation, the width of the fluctuation reduces, and you have kind of steeper lattice, PBI lattice cage due to this cation mixing. As you see, if you see the pictorially in formamidimium lead iodide, if you take this particular area, lead iodide lead, so it fluctuates back and forth, so you have kind of rocking motion here. However, with cesium, you lock the octahedral tilting in a particular orientation, and it does not fluctuate much. So you have kind of less distortion in the structure because of dynamical distortion in the lattice because of this cation mixing. So also we found we try to find that what's happening to FA cations, because that is also quite mobile in ambient temperature and pressure. We found that in formamidimium lead iodide, when we plot the trajectory of nitrogen atoms, let's say in this figure, we can see that it's distributed in all the possible orientations. So it does not have any particular orientation which it's fixed in. So it's a kind of free tumbling motion or vibrational motion it's undergoing in formamidimium lead iodide. But when we have cation mixing, we can see the cage is distorted, and it forces the FA cations to be oriented in particular orientation, and because of that, you can see these sphere becomes a kind of two lobes where the nitrogen atoms spend the time most. So with that, you can understand that the FA cations have particular orientation because of this cation mixing in this lattice. So these can affect the carrier lifetime, but it's we have not done so far anything. It's and also this particular topic is a bit of in debate. So look into the other properties. So how these distortion can affect the electronic properties of our mix cation of these perovskites. We first look into the band gap, and we found that as we mix cesium in the formamidimium, we have a blue shift in the band gap, and as you can see, it's small, but you have systematic increase from cesium cesium very small concentration to 25% cesium. When we look into the how the frontier bands are changing, we found that valence band maxima get downshifted when we increase the cesium concentration, whereas the conduction band get higher energy. So as a whole, it split it increased the band gap, and the band gap get blue shifted. We also look into how the chemical bonding nature is changing with this cation mixing. First of all, we see for valence band, which is anti-bonding between the lead 6s and iodine 5p orbitals. It's a covalent in nature, as you can see here. They are kind of anti-bonded, and because of this distortion, you can see there's the iodine is kind of not linear to the lead 6s orbitals now, and that type of distortion increase the kind of reduce the overlap between these anti-bonding orbitals, and that gives you the extra stability which you are finding here. As you can see, with cation mixing, you get kind of downshift, that is kind of stability of your valence band. On the other hand, if you focus on the conduction band, it's a non-bonding lead 6s p orbital, as you can see here. And for formamidimium lead iodide, it's pretty ionic in nature. But when we have incorporated cesium in it, it's the conduction band is more covalent in nature now, because as you can see, this is the contribution of the iodine, and this is pretty much clear that it start contributing to the conduction band. So it's not purely, it's not as ionic as it was before, and you have covalency in the conduction band here. And as it's inherently it was a valence, it was a ionic bond. As you are increasing the covalency in this type of bond, it's destabilizing as a whole, and getting it's shifting in a higher energy. Also, we look into the band structure of it in high symmetry points. When we incorporated the spin orbit coupling, we found that for high symmetry, that is formamidimium lead iodide in the left side, as you can see, it's not it's splitted, but it's not that much. Splitting is not that much because it's in high symmetry still. But when we break the symmetry by incorporating cesium in it, you can see the the conduction band splits a lot, I mean, compared to the formamidimium lead iodide, and that tells you that with cation mixing, you have kind of Rashba-type splitting more prominent in the structure. Now the factor is here, as you can see, this the amount of the energy scale of this particular splitting is not very high, so we really don't know how much it will affect the charge carrier recombination. But this is a way experimentally, as well as we can think of getting kind of indirect band gap in the in these type of perovskite materials, which eventually can give you some sort of increase in the recombination time. Also, we coming to the second topic, which is dealing with the phase transition. We look into the formamidimium lead iodide phases, and we found that depending on the temperature and how you are treating your sample, you can have different type of phases, you can have hexagonal phases, which is again blue phase as it called, and it's not a photoactive. Also, you can have cubic and tetragonal formamidimium lead iodide. Interestingly, recently it has been found that depending on the temperature of the temperature of the formamidimium lead iodide in its perovskite phase, the cation dynamics also can change a lot. So with that in background, we try to find the energetics of the competing phases, and also we try to find how these phases can affect the structural dynamics. So first we look into the, as you can see here, the most three prominent phases here is a cubic, tetragonal, and hexagonal. So we take these three structures for our computational studies, and we found that as we know, hexagonal has a kind of phase sharing octahedras, so they form the chain of PBI, and then tetragonal and cubic are corners, are the other type, so they have this octahedra, and the iodines are corner sharing here. So if we take the energetics, the most stable is the hexagonal, then the tetragonal, and the most unstable is the cubic. And here is the energy values, how much they are stable or destabilized corresponding to other phases. So also these particular values we got from static calculation, that is density functional theory calculations, but we also try to find that what's happening when we are doing molecular dynamics calculation. I found that the in a finite temperature and pressure also, these particular order of stability, that is the hexagonal is the most stable, then tetragonal, then cubic, is written for these during the dynamics calculation as well. So we try to find why exactly is this happening, means why we have different phase in different energies. And we found that for cubic, as you can see, these are corner sharing, and for hexagonal this is a chain of lead, and PBI angles are 180 degree, whereas the PBI PB angles are 77 degree in hexagonal phases. So but the bond length does not change much for these two phases. So we can understand that this is just because of this how the octahedra are attached to each other. So as this is phase sharing in hexagonal phases, they are much more stable and than the cubic phase, which is corner sharing. Then we also try to find the two corner sharing phases, what's happening there, and all we found that PBI PB angles are much smaller in the tetragonal phases, and that we can rationalize in the fact which we discussed before, that the if you see the lead iodide lead bond bonding, it's anti-bonding. So and it's mostly overlapped when you have 180 degree in your the angle, but when you distort your lattice, the anti-bonding overlap reduces, and that can eventually increase your stability in the structure. So this is another nice finding, that if you really have distorted structure in the formamidimium lead iodide, it can be, it depends on how much your lattice is distorted, but it can be much more stable than the high symmetric cubic phases. We also found out the band gaps, and as you can see, the hexagonal phases are 2.89 electron volt, that is not photovoltaically active region, so it's a wide gap. But for cubic and tetragonal, we have found a nice match with the experiments, and it's 1.5 around. So these two tetragonal and cubic phases are photoactive. We look into the A-cation dynamics as well. So in 300 Kelvin, as I showed before also, we don't find any kind of particular orientation of formamidimium inside the cage. So you have particular no particular orientations of formamidimium, and it rotates kind of freely. But when we reduce the temperature at 200 Kelvin, this is a tetragonal phase, you can see two changes. So one is the PBI are much more distorted than the cubic phase, and also the FA-cations. This is the trajectory of FA-cations, and you can see this is kind of located in particular space and oriented in a particular direction. So we conclude that local cation dynamics in formamidimium, it's can drastically change over temperature and phases, and beta, that is tetragonal formamidimium lead iodide, has anisotropic cation dynamics, that is the cations are now oriented in a particular orientation direction, and it shows orientation preferential orientations. We also try to find whether there is a long range ordering in the formamidimiums, and we found in beta phase, that is tetragonal phase, we found that two formamidimium cations are can be at 90° to each other, and when we calculate the dihedral angle, as you can see, it's more or less it fluctuates, but more or less it stays in the 90°. So pictorially, if you see, this is two molecular vectors are oriented 90° to each other in nearest neighbor cages. So it has a kind of ordering of formamidimium in the low temperature phases. But as I showed, in 300 Kelvin, we don't see this type of long range ordering of formamidimium cations. We went ahead and calculated the rotational relaxation of formamidimium cations, and for that we calculated vector autocorrelation function. And as you can see, for alpha, this just to say physically, the vector autocorrelation function signifies how quickly your particular, let's say for here it's a molecular vector, get randomized. So when you start from a particular orientation, how quickly it gets randomized over time, that gives you the vector correlation function. So considering the nitrogen, this molecular axis as the molecular axis of our calculations, we found that in the formamidimium, in the alpha phase, you have pretty quick randomization of these molecular vectors. However, at beta phase, you cannot see, it's kind of correlated, and it does not decorrelate in during our simulation at all. So this again tells us that cation relaxation in beta phase, that is tetragonal phase, is much more slow than the alpha phase. And to find out the relaxation time, which experimentally can be found from NMR experiment, we fit this data with the non-exponential functions, that is stretch exponential function, and we found that 8.8 for alpha phase, you find a relaxation time of 8.8 picosecond. This matches very well with the recent experimental data. So with this, we conclude that cation motion is much more restricted in the low temperature phase, that is tetragonal phase, than the alpha phase, which is 300 Kelvin phase. So coming to the last topic of this discussion, that is how we can change the how we can substitute lead in the hybrid perovskites. So as we know that lead is toxic in nature, so it's good to have some other element which will be giving as good efficiency as lead based perovskites, but not containing lead. And if you see a periodic table, you have lead in the it's a pretty heavy element, but as we can't use it, the idea of what we have with our collaborators is to replace it with tin and germanium, so which are lighter than the lead, but in the same group. So for that, we took from methylammonium lead iodide initially and replaced this lead with tin and germanium, and tried to find that what exactly happening, is it stable or not, or what's the optoelectronic property of these materials. So when we calculated the stability, we found that comparing to its degraded product, that is iodide salt of its methyl iodide or tin iodide or germanium iodide, you can find all these materials are quite stable in inert condition. So we have not gone for any kind of atmospheric calculations. So that is another level of complication in computation. So that's undergoing project now. But interestingly, we found that if you take the inert atmosphere as your working condition, so all these are quite stable than its degraded product. So you can have kind of thermodynamic stability here. And also we another interesting thing, we found that when we mix germanium in tin, we find a reduction in the stability. So that signifies that maybe it's better to have kind of only tin or only germanium as our perovskite, not the mixed one, because they are not as stable as the parent compounds. So, but interestingly, we found that when we replace tin to germanium, we find tuning of the band gaps, and this band gap tuning can be really interesting to use it for different type of purposes, like tandem solar cells, where you can have different type of band gap materials in different layer, and to absorb different spectrum of the sunlight. We also calculated the effective mass and found that only tin compounds are pretty gives pretty small effective mass. That signifies that it can have high mobility in the material, but germanium containing materials are not as good as tin. And with all these, we concluded that this type of tin germanium mix systems can be stable and can be used as the substitution of lead based perovskites. But it's again, we know that these tin germanium type of systems suffer a lot from oxidations, and that we need to find a way to stop its oxidation and degradation in other way. With that, I conclude my webinar by giving a summary of we have atomic scale insights of different type of cation and B metal mixing. So we have found that these substitution or chemical composition engineering can really affect the structure as well as electronic and optical properties of the perovskites. With compositional engineering, we can increase the hydrogen bonding that can enhance the stability. So this is another factor which we can really look into it and find another way to stabilize the perovskites. And with cation mixing, we found there is a reduction in the temperature. We found a reduction in the dynamics. And that can change the photovoltaic behavior, but how, we still don't know. But we can definitely, we have a effect because of this cation mixing there. Also, we can have lead free perovskite materials for solar cells by substituting it with tin and germanium, and that can give you very interesting photovoltaic and photovoltaic properties. But again, we need to do more research on it to make it stable and much more resistant towards the atmospheric factors. With that, I thank my supervisor, Professor Alison Barker, and Professor Islam, who constantly encourage me to research on this area. And I also thank ECHO for funding all my collaborators, and Archer and Belena for all the computational times. And with that, this is the list of publications we have managed to publish in last few years. And with that, thanks for your all attention, and I'll be happy to have questions.
Okay, thank you very much.
Thanks.
Are there any questions? You can raise your hand, or you can write your questions on the directly on the GoToWebinar platform, so don't hesitate. Otherwise, this webinar will be available on our YouTube channel in the webinars, and don't hesitate to send us any questions by mail if you need. Otherwise, I really thank you for this presentation and for your participation, and see you very soon for the next webinar of ECO.
Okay, yeah.
Bye.
Bye.